Somewhere, right now, the universe is getting larger, not in the way a balloon expands when filled with air, pressing outward against some boundary. There is no boundary, there is no edge. Space itself is stretching, quietly and continuously, in every direction, at every point, carrying everything within it further and further apart. Galaxies that were once closer together are now separated by distances that grow with every passing moment. Light that left a distant star billions of years ago has been traveling through a universe that has been expanding the entire time, so that by the time it reaches us, the space it crossed is already far greater than the distance it originally set out to travel. The universe does not expand into something. It simply becomes more of itself. For most of the 20th century, this expansion was considered a settled matter. Edwin Hubble's observations in the 1920s confirmed that galaxies were moving away from one another, and that the further a galaxy was, the faster it appeared to recede. The universe was growing, that much was certain. But the question that followed seemed equally straightforward. Gravity, the force that pulls all matter toward all other matter, should be working against that expansion. Every galaxy tugging on every other galaxy, every particle of matter exerting its pull. Over billions of years, this gravitational drag should be slowing the expansion down, gently but persistently, like friction gradually reducing the speed of a ball rolled across a long surface. The question scientists asked was not whether the expansion was slowing, it was how quickly. Some models predicted the universe would eventually stop expanding altogether and begin to contract, collapsing back on itself in a reversal of the Big Bang. Others suggested the expansion would slow but never fully stop, coasting forward at an ever-decreasing rate for eternity. The answer, scientists believed, could be found by measuring the expansion rate at different points in cosmic history. If you could determine how fast the universe was expanding billions of years ago and compare that to how fast it is expanding now, you could calculate how much gravity had slowed things down. The math was clear, the physics was understood. The only thing missing was precise measurement. In the late 1990s, two independent teams of astronomers set out to make exactly that measurement. They used a particular type of stellar explosion called a Type Ia supernova. These events are extraordinary because they produce a remarkably consistent peak brightness, which means astronomers can use them as reliable distance markers. By observing how bright a Type Ia supernova appears from Earth and comparing that to how bright it should be, scientists can calculate how far away it is, and by measuring how much the light from that supernova has been stretched by the expansion of space, a phenomenon called redshift, they can determine how fast the universe was expanding at the time the light was emitted. The two teams, the Supernova Cosmology project, led by Saul Perlmutter, and the High-Z Supernova Search team, led by Brian Schmidt and Adam Rees, expected to confirm what nearly everyone assumed: the expansion was decelerating. Gravity was winning, slowly but surely. The data would simply tell them by how much. But when the results came in, they did not confirm the expected answer. They contradicted it. The distant supernovae were dimmer than they should have been, not by a small margin that could be attributed to measurement error or dust interference, but by a consistent, unmistakable amount. The only explanation that fit the data was that those supernovae were further away than the standard decelerating model predicted. The universe had not been slowing down, it had been speeding up. The expansion of the universe was accelerating. Both teams arrived at the same conclusion independently, using different telescopes, different analysis methods, and different supernovae. The result was the same. Something was pushing the universe apart faster and faster, overwhelming the gravitational pull of all the matter within it. Something that no existing theory had predicted. Something that no instrument could directly detect, something that, even now, no one can fully explain. Scientists gave it a name. They called it dark energy, not because they understood it, but because they needed a word for the thing they had discovered was there. That discovery, confirmed in 1998 and recognized with the Nobel Prize in Physics in 2011, did not simply add a new detail to our picture of the universe. It overturned the picture entirely. In a single set of observations, the cosmos went from a place governed by matter and gravity, alone, to a place dominated by something altogether different, something invisible, something pervasive, something that makes up roughly 68% of the total energy content of the observable universe, yet remains one of the least understood phenomena in all of physics. This is the story of that discovery. It is the story of the evidence that supports it, the scientific models that attempt to explain it, and the questions it raises about the future of everything that exists. It begins not with an answer, but with a question that is still, after more than 2 decades, waiting to be resolved. What is dark energy, and why is it pulling the universe apart? To understand why the discovery of dark energy was so disorienting, it helps to understand how confidently scientists believed they already knew the story of the universe. By the middle of the 20th century, cosmology had achieved something remarkable. A field that had once been almost entirely speculative, built on philosophy and geometry and careful observations of the night sky, had been transformed into a precise mathematical science. The universe was no longer a mystery to be contemplated. It was a system to be measured, and the measurements, for the most part, were telling a consistent and deeply satisfying story. That story began with Albert Einstein. In 1915, Einstein published his general theory of relativity, a framework that redefined gravity not as a force pulling objects toward one another, but as the curvature of space and time caused by the presence of mass and energy. Massive objects bend the geometry of the space around them, and other objects follow the curves of that bent geometry. Planets orbit stars, not because they are pulled by an invisible rope, but because the star has curved the space through which the planet moves. General relativity was extraordinarily successful. It explained phenomena that Newtonian gravity could not, including the precise orbit of Mercury and the bending of starlight around the Sun, both of which were confirmed by observation. But when Einstein applied his equations to the universe as a whole, he encountered a problem. His equations predicted that the universe could not be static. It had to be either expanding or contracting. There was no stable middle ground. The geometry of space, shaped by all the matter within it, demanded change. Einstein did not accept this. In 1917, the scientific consensus held that the universe was eternal and unchanging. The idea that it might be expanding or collapsing seemed absurd, unsupported by any observation. So Einstein introduced a term into his equations, a constant, which he represented with the Greek letter lambda, designed specifically to counteract gravity and hold the universe still. This term, later known as the cosmological constant, acted as a kind of repulsive pressure built into the fabric of space, perfectly balancing the attractive pull of gravity so that the universe neither grew nor shrank. It was a mathematical fix, elegant in its simplicity, but motivated not by evidence, only by the assumption that the universe must be static. Einstein himself would later express deep reservations about it, though the exact nature and timing of those reservations has been debated by historians of science. The correction did not last long. In 1922, the Russian physicist Alexander Friedmann showed that Einstein's equations, without the cosmological constant, naturally described a universe that could expand or contract depending on its contents. Friedmann's solutions were purely theoretical. He had no observational evidence to support them, but the mathematics was rigorous and, It opened a door that Einstein had tried to keep closed. Then, in 1927, the Belgian physicist and Catholic priest Georges Lemaitre independently derived similar solutions and went further. He proposed that the universe was not only expanding, but that it had originated from a single primordial state, an initial moment of extraordinary density and temperature from which everything had emerged. Lemaitre called it the primeval atom. The idea was radical, and many scientists dismissed it, but it was mathematically consistent with general relativity, and it made specific predictions about how galaxies should be moving relative to one another. The observational confirmation came from Edwin Hubble, working at the Mount Wilson Observatory in California. Hubble had been measuring the distances to galaxies using Cepheid variable stars, a type of pulsating star whose brightness is directly related to its pulsation period, making it a reliable distance indicator. When Hubble combined his distance measurements with the redshift measurements that other astronomers had been collecting, measurements showing that the light from distant galaxies was systematically shifted toward longer, redder wavelengths, the pattern was unmistakable. Galaxies were moving away from us. The farther away a galaxy was, the faster it was receding. The universe was expanding. This relationship, now known as Hubble's law, was published in 1929, and it changed cosmology forever. The static universe was gone. The cosmological constant, introduced to preserve it, appeared to be unnecessary. Einstein reportedly abandoned the term, and for decades afterward, the cosmological constant was treated as a historical curiosity, a cautionary tale about allowing philosophical preference to override mathematical prediction. What followed was a golden era of cosmological progress. If the universe was expanding, then running the expansion backward implied that everything had once been compressed into an unimaginably hot, dense state. This was the foundation of what would come to be called the Big Bang Theory. In 1948, the physicists Ralph Alpha and George Gamow predicted that this initial hot state should have left behind a faint glow of radiation, cooled by billions of years of expansion into microwave wavelengths, filling the universe in every direction. In 1964, Arno Penzias and Robert Wilson, working at Bell Laboratories in New Jersey, accidentally detected exactly that a uniform background of microwave radiation arriving from every direction in the sky, with a temperature of approximately 2.7 degrees above absolute zero. The cosmic microwave background radiation, as it became known, was the echo of the Big Bang. Its discovery cemented the Big Bang model as the standard framework for understanding cosmic history. By the 1980s and 90s, cosmology had assembled a remarkably detailed picture. The universe had begun in an initial singularity, approximately 13.8 billion years ago. It had expanded and cooled. Subatomic particles formed. Hydrogen and helium nuclei emerged within the first few minutes. Hundreds of thousands of years later, the universe cooled enough for atoms to form, releasing the cosmic microwave background. Over hundreds of millions of years, gravity pulled matter together into the first stars, the first galaxies, and eventually the large-scale structures we observe today. The remaining question, the question that seemed so manageable in the 1990s, was about the future. How would the expansion end? Gravity was the only long-range force acting on the largest scales, and gravity always attracts. Every galaxy pulls on every other galaxy. Every atom of matter exerts a gravitational tug on every other atom. The expansion might be happening, but gravity should be relentlessly decelerating it. The only unknowns were the rate of deceleration and the total amount of matter in the universe. If the universe contained enough matter, gravity would eventually halt the expansion and reverse it, leading to a collapse, sometimes called the Big Crunch. If the universe contained less matter, the expansion would continue forever, gradually slowing, but never quite stopping, coasting outward for eternity. Either way, the trajectory was the same. The universe was decelerating. The only question was how much. This was the scientific consensus that the two supernova teams set out to refine, not to overturn, not to challenge, simply to measure more precisely. The tools were better than ever. Charge-coupled devices had replaced photographic plates, allowing far more sensitive and accurate measurements of distant light. Computer algorithms could process enormous datasets. Telescopes had grown more powerful. The Type Ia supernovae were understood well enough to serve as standardizable candles objects whose intrinsic brightness could be calibrated so that their apparent brightness would reveal their true distance. Everything was in place. The physics was understood. The mathematics was established. The observations were achievable. And the answer, everyone assumed, would confirm what gravity demanded. The universe was slowing down. That assumption was the foundation of modern cosmology. It was built on decades of successful theory, confirmed by multiple independent observations, and supported by the most fundamental force in nature. And in 1998, it was proven wrong. The universe was not decelerating. It was accelerating. Something was overpowering gravity on the largest possible scale. Something that the entire framework of 20th century cosmology had not anticipated, had not predicted, and could not explain. The confident story of the universe, the story that had been assembled with such care over nearly a century, was suddenly incomplete. The two teams that discovered the accelerating expansion did not set out to revolutionize cosmology. They set out to measure a number, a single number called the deceleration parameter that would quantify how quickly gravity was slowing the expansion of the universe. The deceleration parameter was expected to be positive. A positive value would mean the expansion was losing speed, exactly as gravitational physics predicted. The only question was the magnitude. A large positive value would suggest the universe had enough matter to eventually halt and reverse the expansion. A small positive value would suggest the expansion would continue forever, gradually approaching but never reaching zero velocity. Either outcome was scientifically interesting, but neither was surprising. The method both teams chose relied on Type Ia supernovae. These are not ordinary stellar explosions. An ordinary supernova occurs when a massive star exhausts its nuclear fuel and its core collapses under its own gravity, triggering a catastrophic rebound that tears the star apart. Type Ia supernovae follow a different path. They occur in binary star systems where one member is a white dwarf, the dense, Earth-sized remnant of a sun-like star that has shed its outer layers and ceased nuclear fusion. If the white dwarf orbits closely enough to a companion star, it can gravitationally pull material from that companion onto its own surface. As this stolen material accumulates, the white dwarf grows heavier. When its mass approaches a critical threshold, known as the Chandrasekhar limit, approximately 1.4 times the mass of the Sun, the conditions at its core become extreme enough to ignite a runaway thermonuclear explosion that destroys the entire white dwarf in a matter of seconds. The physics of this process is what makes Type Ia supernovae so valuable to cosmologists, because the explosion is triggered at a consistent mass threshold. The energy released is remarkably uniform. Every Type Ia supernova produces roughly the same peak luminosity. This does not mean they are all perfectly identical. There are variations in brightness that depend on the composition of the white dwarf and the details of the explosion, but astronomers discovered that these variations follow a predictable pattern. Brighter Type Ia supernova fade more slowly, and dimmer ones fade more quickly. By measuring how quickly the light curve declines after peak brightness, astronomers can calibrate each supernova's true luminosity with impressive precision. This relationship known as the Phillips relation after the astronomer Mark Phillips, who formalized it in 1993, transformed Type Ia supernovae into what astronomers call standardizable candles, objects whose intrinsic brightness can be reliably determined, regardless of where they are in the universe. Once you know how bright a supernova truly is, and you measure how bright it appears from Earth, the difference tells you how far away it is. Light dims with distance. According to a precise mathematical relationship, a supernova that appears 4 times dimmer than expected is twice as far away. The distance measurement, combined with the redshift of the supernova's light, reveals the expansion rate of the universe at the time the supernova exploded. By gathering supernovae at a range of distances and therefore a range of cosmic epochs, you can map how the expansion rate has changed over time. If the expansion has been decelerating, distant supernovae should appear slightly brighter than they would in a uniformly expanding universe, because the universe was expanding faster in the past and has since slowed down, meaning the supernovae are slightly closer than a constant expansion rate would predict. This was the measurement both teams set out to make. The Supernova Cosmology project, based at the Lawrence Berkeley National Laboratory in California and led by Saul Perlmutter, had been developing techniques for systematically discovering distant supernovae since the late 1980s. Their approach was methodical and industrial. They would reserve time on large telescopes, image wide fields of sky, then return to the same fields weeks later to look for new points of light that had appeared in or near distant galaxies. Each new point of light was a supernova candidate. Follow-up observations with spectroscopy would confirm whether the candidate was a Type Ia supernova and measure its redshift. Over years of refining this approach, the team built a pipeline capable of discovering dozens of distant supernovae in a single observing run. The High Z Supernova Search Team, an international collaboration led by Brian Schmidt at the Australian National University, with Adam Rees playing a central role in the data analysis, used a similar but independently developed strategy. They too hunted for distant Type Ia supernovae, confirmed them spectroscopically, measured their light curves, calibrated their luminosities, and calculated their distances. The two teams were competitors. They used different telescopes, different software, different analysis pipelines, and different calibration methods. They were aware of each other's work but operated. This independence would prove crucial, because when both teams reached the same unexpected conclusion, it became far harder to dismiss the result as a systematic error belonging to one particular method. By 1997 and 1998, both teams had accumulated enough distant supernovae to measure the deceleration parameter with meaningful precision. The data was processed, the light curves were calibrated, the distances were calculated, and the results were plotted against the predictions of different cosmological models. The supernovae were too dim, not by a dramatic margin, not by a factor that screamed error, but by a consistent, statistically significant amount that could not be attributed to known sources of uncertainty. The distant Type Ia supernovae were fainter than the decelerating models predicted. Fainter meant farther. Farther meant the universe had expanded more than expected between the time the supernovae exploded and the present day. And the only way the universe could have expanded more than a decelerating model predicted was if the expansion had not been decelerating at all. It had been accelerating. The implications were immediate and unsettling. If the expansion was accelerating, then something was actively driving it, not just the residual momentum from the Big Bang, but an ongoing force or pressure that was pushing space apart faster and faster. Gravity alone could not produce acceleration. Gravity only attracts. Whatever was causing the acceleration had to act in the opposite direction, behaving as a kind of repulsive influence that operated on the largest scales of the universe. Both teams were cautious. They understood that an extraordinary claim required extraordinary evidence, and they subjected their data to every test they could devise. Could interstellar dust be dimming the supernovae, making them appear farther away than they really were? Dust does dim light, but it also reddens it by scattering shorter wavelengths more than longer ones. The teams checked for this reddening signature and found that it could not account for the observed dimming pattern. Could the type Ea supernovae at high redshift be intrinsically different from nearby ones? Perhaps because the chemical composition of the universe was different billions of years ago. This was a legitimate concern, and both teams examined it carefully, comparing the spectral properties and light curve shapes of distant supernovae with those of well-studied nearby supernovae. The distant supernovae showed no systematic differences that could explain the anomaly. Could gravitational lensing the bending of light by intervening mass be distorting the measurements? Lensing can both brighten and dim distant objects, but its effects should average out over a large enough sample, and the observed dimming was too consistent and too systematic to be explained by random lensing. One by one, the alternative explanations were tested and found insufficient. The conclusion held. The data from two independent teams, using different instruments, different analysis techniques, and different supernova samples, converged on the same result. The expansion of the universe was accelerating. The deceleration parameter was not positive, it was negative. Adam Riess later described the experience of seeing the result emerge from the data as a sense of dread rather than excitement. The finding was so unexpected, so contradictory to the established framework, that the first instinct was to look for mistakes. When no mistakes could be found, the reality of the discovery slowly settled in. The universe was not behaving the way it was supposed to. The two papers were published in 1998, one from each team. The supernova Cosmology project's results appeared in the Astrophysical Journal in 1999, and the High Z team's paper, with Adam Riess as lead author, was published in the Astronomical Journal in 1998. Together, they presented the scientific community with a result that demanded explanation. Something was causing the universe to accelerate, something enormous, pervasive, and entirely unknown. Within the scientific community, the response was a mixture of skepticism and fascination. The data was strong, but the implication was extraordinary. If the expansion was truly accelerating, then the majority of the energy content of the universe was in a form that no one had directly detected, no one had predicted from fundamental physics, and no one could explain. The name given to this unknown component, dark energy, was not a description. It was a placeholder, a label for ignorance wrapped in the language of physics. The discovery did not close a chapter in cosmology. It opened one that remains unfinished. And everything that has followed, every observation, every model, every telescope designed to study the expansion, has been an attempt to understand what the supernova data revealed in those quiet, disorienting months at the end of the 20th century. If the accelerating expansion had rested on supernova data alone, the scientific community might have remained skeptical for years. A single line of evidence, however compelling, can always be questioned. Instruments drift, calibrations carry hidden assumptions. Astrophysical objects that appear uniform may harbor subtle variations that only reveal themselves with better data. The supernova teams had been thorough, but thoroughness does not eliminate the possibility that some unknown systematic effect could be mimicking the signature of acceleration. What transformed dark energy from a provocative hypothesis into an accepted component of the standard cosmological model was not a single confirmation, but a convergence of entirely independent observations, each pointing toward the same conclusion from a completely different direction. The first and perhaps most powerful confirmation came from the cosmic microwave background, the faint afterglow of the Big Bang that fills the universe in every direction. This radiation was released approximately 380,000 years after the beginning, at the moment when the universe had cooled enough for electrons and protons to combine into neutral hydrogen atoms, allowing photons to travel freely through space for the first time. Those photons have been traveling ever since, stretched by the expansion of space from their original visible and infrared wavelengths into the microwave range. Today, the cosmic microwave background has a nearly uniform temperature of approximately 2.725 degrees above absolute zero. But embedded within that uniformity are tiny fluctuations, variations on the order of 1 part in 100,000 that encode an extraordinary amount of information about the early universe. These fluctuations are not random. They carry a specific pattern of angular sizes and amplitudes that depends on the physical conditions of the early universe, including its total energy density, its geometry, its matter content, and its expansion history. By measuring the pattern of these fluctuations with sufficient precision, scientists can determine the fundamental parameters of the universe with remarkable accuracy. The first detailed all-sky map of these fluctuations came from the Cosmic Background Explorer satellite, known as COBE, which operated in the early 1990s. COBE confirmed that the fluctuations existed and that their overall properties were consistent with the Big Bang model. But COBE's angular resolution was limited. It could detect the broad features of the fluctuation pattern, but could not resolve the finer details needed to measure cosmological parameters precisely. That changed with the Wilkinson Microwave Anisotropy probe, known as WMAP, launched by NASA in 2001. WMAP mapped the cosmic microwave background with far greater precision than COBE, measuring the angular power spectrum, the statistical distribution of fluctuation sizes across the sky, with enough detail to determine the geometry and composition of the universe. The results were striking. The fluctuation pattern indicated that the universe is geometrically flat, meaning that the total energy density of the universe is very close to a specific critical value predicted by theory. But when WMAP measured how much of that total energy density was contributed by ordinary matter and dark matter combined, the answer was only about 32%. The remaining 68% had to be something else, something that contributed to the total energy density of the universe, but was neither ordinary matter nor dark matter. This missing component was entirely consistent with dark energy. The cosmic microwave background did not directly detect the acceleration of the expansion. It measured something different, the geometry and composition of the universe, at a time long before the acceleration became dominant. But the numbers aligned precisely. If you took the matter content measured by WMAP and added the dark energy density required by the supernova observations, the total matched the critical density needed for a flat universe. Two completely independent measurements, probing entirely different epochs of cosmic history, using entirely different physics, arrived at the same composition. The universe was approximately 68% dark energy, 27% dark matter, and 5% ordinary matter. The European Space Agency's Planck satellite, launched in 2009, later refined these measurements with even greater precision. Planck's map of the cosmic microwave background remains the most detailed ever produced, and its results confirmed and tightened the WMAP findings. The composition of the universe remained consistent. Dark energy dominated. A second independent confirmation came from a phenomenon known as baryon acoustic oscillations. In the earliest moments of the universe, before the cosmic microwave background was released, The cosmos was a hot, dense plasma of matter and radiation. Within this plasma, gravity and radiation pressure competed in a continuous tug-of-war. Gravity pulled matter inward, compressing it into denser regions. Radiation pressure pushed outward, resisting the compression. This competition created sound waves, pressure waves that propagated through the plasma at a significant fraction of the speed of light, spreading outward from every initial overdensity like ripples from stones dropped into a pond. When the universe cooled enough for neutral atoms to form, the radiation decoupled from the matter and the sound waves froze in place. The matter was left with a characteristic imprint, a slight statistical excess of galaxies separated by a specific distance, corresponding to the maximum distance those sound waves had traveled before freezing. This distance, known as the sound horizon, is approximately 150 megaparsecs in today's universe, or roughly 490 million light-years. It acts as a cosmic standard ruler, a known physical length that can be measured at different epochs of cosmic history to determine how the universe has expanded over time. By mapping the three-dimensional positions of millions of galaxies across large volumes of space, astronomers can detect the baryon acoustic oscillation signal as a subtle peak in the statistical distribution of galaxy separations. The Sloan Digital Sky Survey, one of the most ambitious astronomical mapping projects ever undertaken, was among the first to measure this signal clearly by observing the apparent size of the baryon acoustic oscillation feature at different redshifts, and therefore at different times in cosmic history. Scientists could trace how the expansion rate had changed. The results supported the same conclusion. The expansion history of the universe was consistent with a cosmos dominated by dark energy. The baryon acoustic oscillation measurements provided an entirely independent geometric confirmation that something beyond matter and radiation was driving the expansion. A third line of evidence came from the study of galaxy clusters, the largest gravitationally bound structures in the universe. Galaxy clusters form where the density of matter is high enough for gravity to overcome the expansion and pull material together. The rate at which galaxy clusters grow over cosmic time depends on the competition between gravity, which promotes growth, and the expansion of space, which inhibits it. If dark energy is accelerating the expansion, then at some point the expansion becomes so rapid that gravity can no longer efficiently gather new material into clusters. The growth of structure effectively stalls. By counting galaxy clusters at different redshifts and comparing the observed growth rate with theoretical predictions, scientists found that structure growth had indeed slowed in the more recent half of cosmic history, exactly the period when dark energy was expected to become dominant. The abundance and distribution of galaxy clusters matched the predictions of a universe with approximately 68% dark energy. Additional support came from gravitational lensing surveys, which measure how the distribution of mass in the universe bends the light from distant galaxies. The pattern of distortion reveals the underlying distribution of both visible and invisible matter, and the evolution of that distribution over time is sensitive to the presence of dark energy. These measurements, too, were consistent with the emerging picture. What made the case for dark energy so powerful was not any single observation, but the fact that multiple independent methods, supernovae, the cosmic microwave background, baryon acoustic oscillations, galaxy cluster counts, gravitational lensing, all converged on the same answer. Each method probed a different physical process, used different instruments, relied on different assumptions, and was sensitive to different potential systematic errors. Yet they all pointed to the same cosmological model: a spatially flat universe composed of approximately 68% dark energy, 27% dark matter, and 5% ordinary baryonic matter, with the expansion accelerating over the past several billion years. This concordance is what elevated dark energy from a surprising supernova result to a pillar of the standard cosmological model known as lambda CDM. Lambda represents the cosmological constant, the simplest mathematical description of dark energy, and CDM stands for cold dark matter. Together, they describe a universe in which the dominant components are both invisible and poorly understood, yet their effects are measured with extraordinary precision. The irony is difficult to overlook. Cosmology had reached a stage where its measurements were among the most precise in all of science. Yet the universe they described was composed almost entirely of things no one could directly see, touch, or explain. 95% of the energy content of the observable universe existed in forms that remained fundamentally mysterious. Dark matter, whose gravitational effects had been observed since the 1930s, at least had the virtue of behaving like matter clumping, attracting, forming structures. Dark energy was something else entirely. It did not clump, it did not attract, it appeared to be a property of space itself, uniform and unchanging, pushing the expansion forward with a constancy that no known physical mechanism could easily explain. The evidence was overwhelming. The existence of dark energy was no longer in serious doubt. But understanding what it actually was, the question remained as open as ever. The observations had defined the problem with breathtaking precision. They had measured its effects across billions of years of cosmic history. They had confirmed its presence through every available method. They simply could not explain it. The observations confirmed that dark energy exists. They measured its effects with precision. They determined that it constitutes roughly 68% of the total energy content of the observable universe. But none of those observations revealed what dark energy actually is. Knowing that something is there and understanding what it is are entirely different achievements. And cosmology found itself in the unusual position of having mapped the dominant component of the universe without being able to identify it. The simplest and most widely discussed explanation is the one that Einstein himself introduced and then abandoned more than a century ago: the cosmological constant. In its modern form, the cosmological constant represents a fixed, uniform energy density inherent to empty space. Not energy carried by particles or radiation, but energy that belongs to the vacuum itself. Every cubic meter of space, no matter how empty it appears, contains the same tiny amount of energy. This energy does not dilute as the universe expands, because it is a property of space rather than something contained within it. As new space is created by the expansion, new vacuum energy comes with it, maintaining a constant energy density everywhere and at all times. The gravitational effect of this vacuum energy is unlike anything produced by ordinary matter or radiation. In general relativity, gravity is determined not only by mass, but by all forms of energy and pressure. Ordinary matter and radiation produce positive pressure and attractive gravity. The cosmological constant produces negative pressure, a kind of tension in the fabric of space that acts gravitationally as a repulsive force. When the density of matter was high in the early universe, gravity dominated and the expansion decelerated. But as the universe expanded and matter became increasingly diluted across ever larger volumes, the constant energy density of the vacuum eventually became the dominant component. At that point, the repulsive effect of the cosmological constant overtook the attractive pull of matter, and the expansion began to accelerate. This transition happened approximately 5 billion years ago. For the first 9 billion years of cosmic history, the universe was matter-dominated. Gravity slowed the expansion, and large-scale structures, galaxies, galaxy clusters, filaments, and cosmic walls grew steadily as matter accumulated under gravitational attraction. Then, as the matter density dropped below the vacuum energy density, dark energy took over. Structure growth slowed, the expansion accelerated, and from that point forward, the universe entered a new phase that will continue indefinitely if the cosmological constant remains truly constant. The cosmological constant fits the observational data remarkably well. Its predictions match the supernova measurements, the cosmic microwave background, baryon acoustic oscillations, galaxy cluster growth, and gravitational lensing surveys. As a mathematical description of dark energy, it is elegant, minimal, and consistent. It adds a single number to Einstein's field equations and produces a cosmological model that agrees with every major observations. But there is a problem, a severe, unresolved problem that has haunted theoretical physics for decades. If the cosmological constant represents the energy of empty space, then quantum mechanics should be able to predict its value. And quantum mechanics does make a prediction, one that is catastrophically wrong. In quantum field theory, empty space is not truly empty. It is a seething landscape of activity filled with virtual particles that constantly appear and disappear in pairs, existing for the briefest moments allowed by the uncertainty principle before annihilating each other. These quantum fluctuations contribute energy to the vacuum. Every quantum field, the electromagnetic field, the electron field, the quark fields, and all others, contributes its own vacuum energy. When physicists calculate the total vacuum energy predicted by quantum field theory, the result depends on assumptions about the highest energy scales at which our current theories remain valid. If those theories hold up to the Planck scale, the energy level at which quantum effects and gravity become equally important, then the predicted vacuum energy density is roughly 120 orders of magnitude larger than the observed value of the cosmological constant. 120 orders of magnitude. That is not a small discrepancy. It is a factor of 10 followed by 120 zeros. It is, by some measures, the largest disagreement between theoretical prediction and experimental observation in the entire history of physics. The vacuum should be seething with so much energy that the universe would have torn itself apart in the first instant of its existence, expanding so violently that no structures, no galaxies, no stars, no atoms could ever have formed. Yet the observed value of the cosmological constant is extraordinarily small, small enough to allow the universe to evolve for billions of years, form structures, produce stars and planets, and only recently begin to accelerate. This discrepancy is known as the cosmological constant problem, and it remains one of the deepest unsolved puzzles in fundamental physics. The calculation itself is not disputed. The quantum field theory prediction, given standard assumptions, genuinely produces that enormous number. The observation, confirmed by multiple independent methods, genuinely produces a tiny number. Something is profoundly wrong with our understanding of how quantum mechanics and gravity interact at the most fundamental level, and no one has been able to resolve the disagreement. Several approaches have been proposed. One possibility is that some unknown symmetry or cancellation mechanism causes the individual contributions from different quantum fields to almost perfectly cancel each other, leaving only the tiny residual value that we observe. This would require an extraordinary degree of fine-tuning, a cancellation precise to 120 decimal places, with no known physical principle to explain why such cancellation should occur. Some physicists find this possibility implausible, though it cannot be definitively ruled out. Another approach comes from string theory, which proposes that the cosmological constant may not have a single predictable value at all. In certain formulations of string theory, the vacuum energy depends on the specific configuration of extra spatial dimensions, and there may be an astronomically large number of possible configurations, a landscape of possible universes, each with its own vacuum energy. In this framework, our universe happens to have a cosmological constant compatible with the formation of structure and the emergence of observers, not because of any deep physical principle, but because only universes with sufficiently small vacuum energy can produce the conditions necessary for complexity. This reasoning, sometimes called the anthropic principle, is deeply controversial. It provides an explanation of sorts, but one that many physicists find unsatisfying because it replaces prediction with selection. It does not explain why the cosmological constant has the value it does. It only explains why we observe a universe with a value small enough to permit our existence. A completely different possibility is that the cosmological constant is exactly zero and the observed acceleration is caused by something else entirely, a dynamic field that changes over time rather than a fixed property of empty space. This idea, broadly known as quintessence, proposes that a new scalar field permeates the universe, slowly evolving as the cosmos expands. Unlike the cosmological constant, which has a fixed energy density, a quintessence field could have an energy density that changes with time, potentially explaining why dark energy became dominant only in the relatively recent cosmic past. The name quintessence was chosen deliberately, echoing the ancient Greek concept of a fifth element, a substance distinct from earth, water, air, and fire that fills the heavens. Quintessence models are mathematically viable and can be constructed to match current observations, but they introduce new parameters and new physics that remain entirely untested. No particle or field corresponding to quintessence has ever been detected. No experiment has identified the specific potential energy function that would govern its behavior. And the observational data, while consistent with quintessence, is equally consistent with a simple cosmological constant. At present, there is no measurement precise enough to distinguish between the two. This is the uncomfortable reality of dark energy research. The observations are exquisite. The measurements are precise. The statistical significance is overwhelming, but the theoretical understanding is fundamentally incomplete. Physicists know what dark energy does. They can describe its effects with mathematical precision. They can predict its influence on the expansion of the universe for billions of years into the future. Yet they cannot explain what it is, where it comes from, or why it has the specific value that it does. The cosmological constant problem is not merely a technical detail awaiting a clever calculation. It sits at the intersection of the two most successful theories in physics, quantum mechanics, and general relativity. And it reveals that those theories are fundamentally incompatible when applied to the vacuum energy of empty space. Resolving this problem may require a new theory of quantum gravity, a framework that unifies quantum mechanics and general relativity into a single, coherent description of nature. Such a theory does not yet exist, despite decades of effort from some of the most brilliant minds in theoretical physics. Until that breakthrough arrives, dark energy remains defined more by what it does than by what it is. It accelerates the expansion. It dominates the energy budget. It resists all attempts at fundamental explanation. And the universe continues to expand, indifferent to the fact that no one yet understands why. The inability to identify dark energy from first principles has not prevented scientists from studying it empirically. Even without knowing what dark energy is, physicists can characterize its behavior by measuring how it influences the expansion of the universe over time. The tool they use for this characterization is a single parameter, denoted by the letter W, known as the equation of state parameter. It describes the relationship between pressure exerted by dark energy and its energy density. This seemingly abstract number carries enormous physical significance because different values of W correspond to fundamentally different types of dark energy, each with profoundly different consequences for the fate of the universe. For ordinary matter, the atoms that make up stars, planets, gas clouds, and human beings, the equation of state parameter is effectively zero. Matter exerts negligible pressure compared to its energy density. For radiation, including photons and other massless or nearly massless particles traveling at or near the speed of light, the equation of state parameter is 1/3. These values are well established and produce familiar gravitational behavior. Matter and radiation both generate attractive gravity and cause the expansion of the universe to decelerate. Dark energy is different. For the cosmological constant, the equation of state parameter is exactly -1. This means the pressure exerted by the cosmological constant is equal in magnitude to its energy density but opposite in sign. A negative pressure that generates gravitational repulsion rather than attraction, a value of W equal to -1, produces a constant energy density that does not change as the universe expands, leading to exponential acceleration that continues indefinitely at a steady rate. This is the simplest possible behavior for dark energy, and it is the prediction of the lambda CDM model that currently serves as the standard framework of cosmology. But W equal to -1 is not the only possibility. If dark energy is not a cosmological constant, but rather a dynamic field like quintessence, then W could take values different from -1 and could even change over time. A quintessence field slowly rolling down a potential energy surface would typically produce a value of W between -1 and -1/3, depending on the shape of the potential and the current state of the field. In such models, the dark energy density would gradually decrease as the universe expands, and the acceleration would eventually slow or even stop at some point in the distant future. There is also a more exotic possibility, one that carries far more dramatic implications. If W is less than -1, dark energy enters a regime that physicists call phantom energy. Phantom dark energy would not merely maintain a constant energy density as space expands. Its density would actually increase over time. As the universe grows larger, phantom energy would grow stronger, accelerating the expansion at an ever-increasing rate. The consequences of phantom energy, if it exists, would be catastrophic on a cosmic scale. The accelerating expansion would eventually overcome every force in nature. First, it would tear apart galaxy clusters, then individual galaxies, then solar systems, then planets, then atoms. In a finite amount of time, the expansion would become infinite, destroying the fabric of space itself in an event known as the Big Rip. The Big Rip scenario is not considered likely by most cosmologists, but it has not been ruled out by observations. Determining whether W is exactly -1, slightly greater than -1, or slightly less than -1 is one of the most important goals in modern cosmology, and it requires measurements of extraordinary precision. Current observational constraints on W are consistent with -1, but the uncertainties are still large enough to permit a range of values. The combined data from supernovae, the cosmic microwave background, baryon acoustic oscillations, and other probes constrain W to be very close to -1, typically within a few percent. But a few percent is the difference between a cosmological constant and a dynamic field. It is the difference between a universe that accelerates steadily forever and one whose acceleration changes character over billions of years. Narrowing those uncertainties is not a matter of academic curiosity. It is a question about the ultimate fate of everything that exists. Measuring W with sufficient precision is extraordinarily challenging. The differences between competing models are subtle, manifesting as tiny variations in the brightness of distant supernovae, small shifts in the baryon acoustic oscillation scale, or slight changes in the growth rate of cosmic structure over time. Detecting these differences requires not only more data, but better data, larger supernova samples with more precise calibration, deeper galaxy surveys covering larger volumes of space, and more sensitive measurements of the cosmic microwave background and gravitational lensing. Beyond the equation of state, some physicists have pursued an entirely different approach to the dark energy problem. Rather than adding a new component to the universe, whether a cosmological constant or a dynamic field, they have asked whether the observed acceleration could be explained by modifying the laws of gravity themselves. General relativity has been tested with extraordinary precision in the solar system, in binary pulsar systems, and through the detection of gravitational waves from merging black holes and neutron stars. But all of these tests probe gravity in relatively strong field, relatively small-scale environments. On the largest cosmological scales, the scales where dark energy manifests, direct tests of general relativity are far more difficult, and it is at least conceivable that gravity behaves differently than Einstein's equations predict when applied to the universe as a whole. Modified gravity theories come in many forms. One class, known as FA, gravity, generalizes Einstein's field equations by replacing the simple curvature term with a more complex function of the curvature. Depending on the choice of function, these models can produce accelerating expansion without any dark energy at all. The acceleration emerges naturally from the modified gravitational dynamics, making it an intrinsic property of space-time, rather than an effect of an unknown energy component. Another approach, known as Browne-World models, draws on ideas from string theory and extra dimensions. In these models, our observable universe is a three-dimensional surface, or brane, embedded in a higher dimensional space. Gravity can leak into the extra dimensions at very large scales, weakening its influence and mimicking the effect of dark energy from the perspective of observers confined to the brain. These models make specific predictions about how the growth of cosmic structure should differ from the predictions of general relativity, with a cosmological constant providing a potential observational signature that future surveys could detect. Scalar tensor theories represent yet another family of modifications in which gravity is mediated not only by the geometry of space-time, as in general relativity, but also by an additional scalar field that couples to matter and influences the expansion rate. These theories can be constructed to match current observations while predicting subtle deviations from general relativity that might become detectable with improved measurements. The challenge with all modified gravity theories is that general relativity has passed every experimental test with extraordinary precision, and any modification must reproduce all of those successes while also explaining the cosmological acceleration. This is a severe constraint. Many modified gravity models that initially appeared promising have been ruled out by subsequent observations, particularly by the detection of gravitational waves. In 2017, the LIGO and Virgo observatories detected gravitational waves from the merger of two neutron stars, and the electromagnetic counterpart of that merger was observed by telescopes across the spectrum just 1.7 seconds after the gravitational wave signal. This near simultaneous arrival demonstrated that gravitational waves travel at the speed of light to extraordinary precision, a result that immediately eliminated a large class of modified gravity theories in which gravitational waves would propagate at a different speed. The surviving modified gravity models are more constrained than ever, but they have not been entirely eliminated. Some models predict differences that would only become apparent with larger statistical samples or more precise measurements of how cosmic structure grows over time. Distinguishing between dark energy and modified gravity requires measuring not only the expansion history of the universe, but also the growth history. How quickly galaxies and galaxy clusters assembled at different epochs. If dark energy is a substance added to an otherwise standard gravitational framework, then the expansion history and the growth history should be related in a specific, predictable way. If gravity itself is modified, that relationship could be different. Detecting such a discrepancy would be a profound discovery, but it demands a level of observational precision that is only now becoming achievable. This is the current state of the dark energy problem. The observations are precise enough to confirm that the acceleration is real and to constrain the equation of state parameter to be very close to -1, but they are not yet precise enough to determine whether dark energy is a cosmological constant, a slowly evolving field, phantom energy, or an artifact of modified gravitational physics. Each possibility carries different implications for the fundamental nature of space-time, for the relationship between quantum mechanics and gravity, and for the long-term future of the cosmos. The universe has provided the evidence of its own acceleration with remarkable clarity. What it has not provided is an explanation. And so the search continues not with philosophical speculation, but with larger telescopes, deeper surveys, more sensitive instruments, and more precise measurements, all designed to narrow the uncertainty surrounding a single parameter that may hold the key to understanding the most dominant and least understood component of reality. The questions surrounding dark energy are not waiting for theoretical breakthroughs alone. A new generation of observational programs, designed specifically to study the accelerating expansion with unprecedented precision, is already reshaping what scientists know and narrowing the space in which answers might be found. These are not small incremental improvements. They represent the most ambitious astronomical surveys ever attempted, each one engineered to measure the expansion history and the growth of cosmic structure with a level of detail that was unimaginable when the supernova teams first published their results at the end of the 20th century. Among the most significant is the Dark Energy Spectroscopic Instrument, known as DESI, installed on the 4-meter Nicholas U. Mayall telescope at Kitt Peak National Observatory in Arizona. DESI is designed to create the largest three-dimensional map of the universe ever assembled. Its focal plane contains 5,000 robotic fiber positioners, each capable of independently targeting a specific galaxy or quasar in the telescope's field of view. In a single observation, DESI can simultaneously capture the spectra of 5,000 objects, measuring both their redshifts and their spectral properties. Over the course of its 5-year survey, DESI aims to measure the redshifts of approximately 40 million galaxies and quasars, spanning a volume of space that stretches back more than 11 billion years of cosmic history. The primary science goal of DESI is to measure baryon acoustic oscillations at many different redshifts, with far greater statistical precision than any previous survey, by tracing how the characteristic baryon acoustic oscillation scale changes across cosmic time. DESI can reconstruct the expansion history of the universe in fine detail, mapping how the expansion rate evolved from the matter-dominated era through the transition to dark energy domination and into the present epoch of acceleration. This expansion history is directly sensitive to the equation of state parameter W, and critically, to whether W has changed over time. Early results from DESI, released in stages beginning in 2024, generated considerable attention within the cosmological community. While definitive conclusions require the full dataset and careful systematic analysis, the initial measurements hinted at the possibility that dark energy may not behave exactly as a cosmological constant. Some combinations of the data suggested that W might be slightly different from -1, or that it might have evolved over cosmic time. These hints are tantalizing, but not yet conclusive. The statistical significance remains modest, and systematic uncertainties have not been fully characterized. But the fact that DESI can even approach the sensitivity needed to detect such subtle deviations demonstrates the power of the new generation of surveys. What was once a question that could only be debated theoretically is now becoming an empirical question that observations can address directly. Complementing DESI's ground-based survey is the European Space Agency's Euclid mission, a space telescope launched in July 2023 to a gravitationally stable point, approximately 1.5 million kilometers from Earth. Euclid is designed to survey approximately 1/3 of the entire sky, mapping the shapes, positions, and redshifts of billions of galaxies across more than 10 billion years of cosmic history. Its two primary instruments, a visible light camera for measuring galaxy shapes and a near-infrared spectrometer and photometer for measuring redshifts, work together to probe dark energy through two independent methods. The first method is weak gravitational lensing, as light from distant galaxies passes through the large-scale structure of the universe. The gravitational influence of intervening matter subtly distorts the shapes of those background galaxies. The distortions are tiny, far too small to detect in any individual galaxy, but when measured statistically across millions of galaxies, they reveal the distribution of all matter, both visible and dark, along the line of sight. By mapping how this matter distribution has evolved over time, Euclid can measure the growth rate of cosmic structure, which is sensitive to both the expansion history and the nature of gravity. If dark energy is a cosmological constant, the growth rate follows a specific prediction. If dark energy is dynamic, or if gravity is modified, the growth rate will deviate from that prediction in measurable ways. The second method is galaxy clustering, including baryon acoustic oscillations measured spectroscopically across a vast volume of space. Together, the lensing and clustering measurements provide complementary constraints on dark energy that are far more powerful in combination than either would be alone. Euclid's survey volume, combined with its space-based vantage point, free from atmospheric distortion, gives it sensitivity to the equation of state parameter that surpasses any previous experiment. On the ground, the Vera C. Rubin Observatory, under construction in Chile and expected to begin its primary survey in the mid-2020s, will transform dark energy science through sheer observational scale and tamed after the astronomer, whose work on galaxy rotation curves provided some of the earliest compelling evidence for dark matter. The Rubin Observatory houses an 8.4-meter primary mirror and the largest digital camera ever built for astronomy, a 3.2 gigapixel detector capable of imaging a field of view nearly 40 times the area of the full moon in a single exposure. Over the course of its 10-year legacy survey of space and time, the Rubin Observatory will repeatedly image the entire visible southern sky every few nights, building up an extraordinarily deep, time-resolved map of the universe. For dark energy research, the Rubin Observatory's primary contribution will come through the discovery and monitoring of Type Ia supernovae on an industrial scale. Previous supernova surveys discovered hundreds, or at most a few thousand supernovae suitable for cosmological measurements. The Rubin Observatory is expected to discover hundreds of thousands of Type Ia supernovae over its survey lifetime, providing a statistical sample so large that many of the systematic bulk uncertainties that currently limit supernova cosmology can be beaten down through sheer numbers and careful cross-calibration. In addition, the Rubin Observatory will contribute to weak lensing measurements, galaxy clustering studies, and the detection of galaxy clusters, making it a multi-probe dark energy experiment in its own right. From space, NASA's Nancy Grace Roman Space Telescope, planned for launch in the mid-2020s, will add yet another powerful capability. Named after the astronomer who played a central role in the development of the Hubble Space Telescope, the Roman Space Telescope carries a wide-field infrared camera with a field of view 100 times larger than Hubble's primary camera, allowing it to survey enormous areas of sky with the sharp resolution that only space-based observation can provide. Its dark energy program includes both a supernova survey and a galaxy redshift survey designed to measure baryon acoustic oscillations and the growth of structure at high redshift, probing the epoch when dark energy first began to dominate the expansion. Together, DESI, Euclid, the Vera Rubin Observatory, and the Nancy Grace Roman Space Telescope form the core of what cosmologists sometimes refer to as the Stage I Dark Energy Program, the most powerful combined observational effort ever directed at a single scientific question. Each experiment brings different strengths. DESI provides spectroscopic precision from the ground. Euclid provides space-based lensing and spectroscopy across a third of the sky. The Rubin Observatory provides unprecedented statistical depth and time domain coverage. The Roman Space Telescope provides high-resolution infrared imaging and spectroscopy from orbit. Their datasets, when combined, will constrain the dark energy equation of state with a precision of a few percent or better, potentially distinguishing between a cosmological constant and a slowly evolving field for the first time. Beyond these flagship projects, other experiments contribute important pieces of the puzzle. The South Pole Telescope and the Atacama Cosmology Telescope have measured the cosmic microwave background at small angular scales, detecting the subtle distortions imprinted by gravitational lensing as microwave photons pass through the large-scale structure of the universe on their way to our detectors. The Simons Observatory, currently under construction in the Atacama Desert, will push these measurements further. Future ground-based cosmic microwave background experiments, including the proposed CMB-S4 program, aim to measure lensing of the microwave background with sufficient precision to provide yet another independent constraint on the growth of structure and the properties of dark energy. The sheer scope of this observational campaign is itself a testament to the scientific significance of the dark energy problem. No single experiment can answer the question alone. Each method has its own strengths and its own systematic limitations. Supernovae measure the luminosity distance to specific redshifts, but depend on the calibration of the Type Ia standard candle. Baryon acoustic oscillations measure the angular diameter distance and the expansion rate, but depend on understanding the galaxy bias, the relationship between where galaxies form and where the underlying matter is weak. Lensing measures the matter distribution directly, but is sensitive to the precise measurement of galaxy shapes, which can be distorted by atmospheric effects, telescope optics, and detector properties. Galaxy clusters probe the growth of structure but depend on accurate mass estimates that are themselves uncertain. The power of the Stage I program lies in combining all of these methods, using each one to cross-check the others and to break the degeneracies that limit any single probe. If all methods converge on W equal to -1, with no evidence for time evolution, the cosmological constant will be confirmed as the correct description of dark energy, and the theoretical challenge of explaining its value will become even more urgent. If the methods reveal a value of W different from -1, or evidence for time evolution, the implications will be revolutionary, pointing toward new physics beyond the standard model, possibly involving new fundamental fields, new forces, or new properties of space-time. Either outcome would represent a milestone in the history of science. The question is no longer whether we can measure dark energy precisely enough to distinguish between competing models. The instruments exist, the surveys are underway, the data is accumulating. The question now is what the universe will reveal when measured with sufficient care. Whatever dark energy turns out to be, its consequences for the future of the universe are inescapable. The fate of everything Every star, every galaxy, every structure that exists or will ever exist depends on how dark energy behaves over the coming billions and trillions of years. If its nature can be determined, then the long-term trajectory of the cosmos can be predicted with confidence. If it remains mysterious, then the ultimate destiny of the universe remains an open question, bounded by possibilities that range from quiet dissolution to violent destruction, the most widely accepted scenario, and the one that follows directly from the cosmological constant model is sometimes called the Big Freeze. If dark energy maintains a constant energy density, if W remains precisely -1 for all time, then the acceleration of the expansion will continue indefinitely, growing steadily stronger relative to the ever-diminishing influence of matter. Galaxies that are not already gravitationally bound to one another will be carried apart by the expanding space between them, receding faster and faster until the light they emit can no longer reach us. The observable universe, which currently extends roughly 46 billion light-years in every direction, will gradually shrink in terms of what remains accessible. Distant galaxies will fade from view, their light stretched beyond detection by the relentless expansion. Within our own gravitational neighborhood, the Milky Way and the Andromeda Galaxy are moving toward one another, drawn by their mutual gravity, and are expected to merge in approximately 4 to 5 billion years. The resulting galaxy, sometimes informally called Milkdromeda, along with a handful of smaller companions in the local group, will remain gravitationally bound, even as the rest of the universe recedes beyond reach. For an observer within this merged galaxy, the sky will gradually empty, where billions of galaxies once filled the observable universe. Eventually, only the stars of the local structure will remain visible. The cosmic microwave background, already faint, will be stretched to wavelengths so long that it becomes undetectable. The evidence of the Big Bang itself will fade into silence. Over far longer timescales, the stars within the merged galaxy will exhaust their fuel. The most massive stars burn through their hydrogen in millions of years, but the smallest red dwarfs are extraordinarily efficient, capable of sustaining nuclear fusion for trillions of years. Eventually, even they will dim and cool, becoming faint remnants that emit barely detectable warmth. The galaxy will become a graveyard of stellar corpses, white dwarfs cooling toward absolute zero, neutron stars spinning down into silence, black holes slowly evaporating through a quantum process described by Stephen Hawking in the 1970s, on timescales almost incomprehensible to the human mind scales. Measured in numbers with dozens or hundreds of digits, even the most massive black holes will radiate away their energy and vanish in faint bursts of particles. What remains is a universe of extraordinary emptiness, scattered particles, separated by distances that continue to grow, drifting through a darkness that no longer contains any organized structure, any source of warmth, any mechanism for complexity. This is the Big Freeze, not a dramatic ending, but a gradual, quiet unwinding. A universe that slowly exhausts its capacity for change and settles into a state of maximum entropy from which nothing further can emerge. The Big Freeze is not a violent fate. It is patient. It unfolds across timescales so vast that human civilization, all of recorded history, and even the entire age of the current universe represent only the barest opening moments. There is nothing sudden about it, nothing catastrophic in any human sense. It is simply the logical consequence of an expansion that never stops and an energy supply that is finite. But the Big Freeze depends on the assumption that dark energy is truly constant. If dark energy is dynamic, if its equation of state evolves over time, the future could unfold very differently. One possibility is that dark energy gradually weakens over cosmic time. In some quintessence models, the scalar field driving the acceleration slowly loses energy as it rolls down its potential, causing the repulsive effect to diminish. If this happens, the expansion could eventually decelerate again, returning the universe to a state where gravity dominates. Depending on the total matter content and the details of the quintessence potential, such a universe might continue expanding at a decreasing rate forever, approaching a coasting state, or, in more speculative scenarios, the deceleration could lead to an eventual contraction, a reversal of the expansion that compresses the universe back toward a state of extreme density and temperature. This hypothetical reversal, known as the Big Crunch, was once the leading alternative to eternal expansion before dark energy was discovered. In a quintessence framework, it returns as a possibility, though one that requires specific and currently untestable assumptions about the behavior of the dark energy field. Far more dramatic is the scenario associated with phantom energy, the possibility that W is less than -1. If the dark energy density increases with time rather than remaining constant, the repulsive force grows without limit. The expansion accelerates not at a steady rate, but at an ever-increasing rate, doubling and redoubling in speed over shorter and shorter intervals. In this scenario, the consequences are not limited to the largest cosmological scales. The accelerating expansion eventually overwhelms every force in nature, tearing apart structures of decreasing size in a predictable sequence. First, galaxy clusters are disrupted. The gravitational bonds holding clusters together are relatively weak, and they would be the first structures overcome by the increasing expansion rate. Next, individual galaxies are pulled apart, their stars scattered as the space within them expands faster than gravity can hold them together. Then stellar systems disintegrate. Planets are stripped from their orbits. Eventually, the expansion rate becomes so extreme that even the electromagnetic forces holding molecules and atoms together are overwhelmed. Matter itself is torn apart. In the final moments, space expands so rapidly that the observable universe shrinks to nothing, and the fabric of space-time reaches a singularity of infinite expansion, the Big Rip. The timeline of the Big Rip depends on how far below -1 the value of W actually is. For values only slightly less than -1, the Big Rip would occur tens of billions of years in the future, far beyond any timescale relevant to current human existence. For more extreme values, it could theoretically happen sooner, though current observations constrain tightly enough that any Big Rip scenario, if physically possible at all, lies far in the future. Most cosmologists do not consider the Big Rip the most likely outcome. Phantom energy raises serious theoretical difficulties, including potential violations of fundamental energy conditions in general relativity and instabilities in quantum field theory. But it has not been excluded by observation until W is measured with sufficient precision to conclusively rule out values below -1. The Big Rip remains a logically possible fate for the universe. There are still other possibilities, more speculative and less constrained by current data. Some models propose that dark energy could undergo a phase transition. At some point in the future, a sudden change in its properties, analogous to water freezing into ice. If the vacuum energy of the universe is not in its lowest possible energy state, but rather in a meta-stable state, a local minimum, rather than the true minimum of the energy landscape, then a quantum tunneling event could trigger a transition to a lower energy state. This transition would propagate outward at the speed of light, as a bubble of true vacuum, fundamentally altering the laws of physics within its boundary. Inside the bubble, the properties of particles, forces, and space-time could be completely different from what we observe today. Such an event, sometimes called vacuum decay, would be undetectable before it arrived and unsurvivable after it did. Vacuum decay is considered extremely unlikely on any human timescale, and the conditions required for it to occur are not well constrained, but it represents yet another way in which the nature of dark energy connects to the deepest questions about the stability and permanence of the physical laws that govern our universe. Each of these scenarios, the big freeze, the big crunch, the big rip, vacuum decay, follows from a different assumption about the nature of dark energy. The universe does not reveal its preference through philosophical argument. It reveals it through measurement. The value of W, and whether it changes with time, is not an academic question. It is the question that determines the ending of the story. And right now, in observatories and laboratories and data centers around the world, scientists are working to measure that value with the precision necessary to answer it. Not because the answer will matter on any human time scale, but because understanding the fate of the universe is among the most profound questions a conscious species can ask. The universe produced beings capable of wondering how it will end. And those beings, despite understanding only a fraction of what surrounds them, have built instruments precise enough to begin narrowing the possibilities. The answer is written in the light of distant galaxies, in the pattern of cosmic structure, in the faint echo of the Big Bang. It is there, waiting to be read by anyone patient and careful enough to look. There is something remarkable about the fact that we know dark energy exists at all. Not remarkable in the way of dramatic discoveries that arrive with fanfare and immediate understanding, but remarkable in a quieter, more humbling sense. The dominant component of the universe, the thing that makes up more than 2/3 of everything there is, was entirely unknown until the final years of the 20th century. For the vast majority of human history, and for most of the history of modern science, no one suspected it was there. No theory predicted it. No philosophy anticipated it. No instrument was designed to detect it. It emerged from data that was collected to answer a different question entirely. And the answer it provided was one that no one was prepared to receive. The universe had been expanding for nearly 14 billion years before any conscious being noticed, and it had been accelerating for roughly 5 billion of those years before anyone realized the expansion was speeding up rather than slowing down. The acceleration was not hidden by distance or obscured by complexity. It was happening everywhere, at every moment, on the largest possible scale. Yet it left no obvious trace in the night sky, no visible signature that a casual observer could detect. It required the precise measurement of the dimming of stellar explosions, billions of light years away, the statistical analysis of faint temperature variations in the oldest light in the universe, and the mapping of millions of galaxies across enormous volumes of space. It required centuries of accumulated understanding general relativity, quantum mechanics, nuclear physics, observational astronomy, detector technology, computational analysis, converging on a single, unexpected result. That result did not simplify the picture of the universe. It complicated it profoundly. Before 1998, cosmology was approaching what many scientists felt was a coherent and nearly complete description of reality. The Big Bang model explained the origin. General relativity explained the dynamics. The cosmic microwave background confirmed the early conditions. The formation of galaxies and large-scale structure could be modeled with increasing precision. The composition of the universe appeared to be dominated by matter, with a well-understood expansion driven by the initial conditions of the Big Bang and gradually decelerating under the influence of gravity. The picture was not finished, but the outlines seemed clear. The discovery of dark energy did not erase that picture. Every previous observation remained valid. The Big Bang still happened. The cosmic microwave background still carried its ancient message. Galaxies still formed through gravitational collapse. But the picture was suddenly dramatically incomplete. The universe was not dominated by matter. It was dominated by something else. something that did not clump, did not attract, did not interact with light, and did not correspond to any known particle or field in the standard model of physics. The outlines of the picture remained, but the canvas itself had changed. More than a quarter century has passed since that discovery, and the fundamental nature of dark energy remains unknown. This is not for lack of effort. The intervening decades have produced some of the most precise cosmological measurements in history. The cosmic microwave background has been mapped with extraordinary detail by WMAP and Planck. Baryon acoustic oscillations have been measured across billions of light years by galaxy surveys of increasing scale. Type Ia supernovae have been discovered and calibrated in ever larger numbers. Galaxy clusters have been counted and weighed. Gravitational lensing has been used to map the invisible scaffolding of dark matter across cosmic time. Every one of these observations has confirmed the existence of dark energy and tightened the constraints on its properties, and every one of them has remained consistent with the simplest possible explanation: a cosmological constant with an equation of state parameter equal to -1. Yet consistency is not confirmation. The measurements are precise, but they are not yet precise enough to rule out the alternatives. A slowly evolving quintessence field, a subtle modification of gravity on cosmological scales, phantom energy with an equation of state below -1, all remain within the bounds of observational uncertainty. The next generation of experiments, DESI, Euclid, the Vera Rubin Observatory, the Nancy Grace Roman Space Telescope, is designed to close that gap, to push the precision to the level where the differences between competing models become detectable. Whether those experiments will deliver a definitive answer or reveal new complexities that demand even deeper investigation remains to be seen. What is certain is that the question matters. It matters not because dark energy affects daily life. On Earth, it does not, and will not for billions of years, but because it represents one of the deepest gaps in our understanding of the physical universe. The cosmological constant problem, the staggering discrepancy between the predicted and observed values of the vacuum energy, is not a minor accounting error. It is a signal that something fundamental about the relationship between quantum mechanics and gravity is not understood. Resolving that discrepancy may require a theory of quantum gravity that does not yet exist, or it may require reconceptualizing the nature of space-time in ways that no one has yet imagined. The answer to the dark energy question may reshape physics as profoundly as general relativity reshaped Newtonian mechanics, or as quantum mechanics reshaped classical physics. Or it may not. Science does not promise dramatic revelations on a predictable schedule. It is entirely possible that the next decade of observations will confirm that dark energy is a cosmological constant with an equation of state indistinguishable from -1, that the theoretical explanation for its value remains elusive, and that the mystery persists for generations. Science has encountered such plateaus before, periods where the observations are clear, but the theoretical understanding lags behind, sometimes for decades, sometimes for centuries. The history of science is not a smooth arc from ignorance to understanding. It is a path marked by long stretches of patient accumulation, punctuated by occasional breakthroughs that arrive only when the right questions have been asked and the right tools have been built. What dark energy has already accomplished, regardless of whether its nature is resolved soon, is a correction of perspective. For most of human history, people assumed they understood what the universe was made of: rocks, water, air, fire, stars, planets, empty space, atoms, molecules, radiation. At every stage, the list seemed complete, and at every stage, it turned out to be incomplete. Dark energy is the latest and most dramatic revision. It tells us that the thing we are most certain about the physical substance of the universe is the thing we understand least. The atoms that make up every object we can see and touch constitute barely 5% of the total. The rest is darkness. Not the darkness of emptiness, but the darkness of ignorance, a reminder that the universe is under no obligation to be comprehensible, and that every answer we obtain reveals new questions we did not know to ask. There is comfort in that, if you are willing to find it. The universe is larger than our understanding. It contains more than we have measured, more than we have imagined, and almost certainly more than we will ever fully explain. Dark energy is not a failure of science. It is evidence that the universe still has something to teach, something so fundamental that it resists our most sophisticated instruments and our most powerful theories. The fact that we have detected it at all, that we have measured its effects with such precision, that we have narrowed the possibilities to a handful of competing models, is itself an extraordinary achievement. It means that the question is no longer beyond our reach. It is simply beyond our current grasp. Tonight, while you listen to these words, the universe is expanding. The space between the great clusters of galaxies is growing larger. The light from the most distant objects is being stretched further into the red, carrying with it the signature of an acceleration that no one anticipated and no one yet understands. Somewhere, a photon that left a distant supernova billions of years ago is arriving at a telescope, carrying in its faint glow a tiny piece of information about how the universe behaved in a different epoch. Somewhere, a robotic fiber positioner is swiveling to capture the spectrum of a galaxy whose redshift will contribute one more data point to the growing map of cosmic expansion. Somewhere, a graduate student is staring at a plot, looking for the faintest hint of a deviation from -1. The universe does not rush toward its answers. It unfolds slowly, patiently, across time scales that dwarf every human endeavor. The acceleration that dark energy produces is gentle, imperceptible, on any scale smaller than millions of light years. Noticeable only when measured across billions of years of cosmic history. It is the quietest force in the universe, and the most powerful. It shapes the destiny of everything that exists, yet it announces itself only through the most delicate observations that science can perform. And perhaps that is the most fitting thing about dark energy. It is not loud, it is not dramatic, it does not demand attention. It simply is woven into the fabric of space, present in every cubic meter of the cosmos, shaping the future with a patience that makes the lifetime of stars seem brief. It is the deepest mystery in modern science, and it surrounds us completely, invisibly, silently, in every direction, stretching onward into a future that even the universe itself has not yet decided.